All right, let's go and talk a little bit about how we could heap something. Let's create a heap.cpp file. Good old gvim. Oh, I have to use C++. I have to use C++. Hold on. Not configured all of this. Thought I should have, but I didn't. All right, so we have a bunch of numbers. How do we get some numbers here? Well, we won't do that yet. So we need to put some numbers into an array.
How about the numbers behind us? Behind you?
The numbers behind me. I can put those numbers into an array. Okay.
Make your life easy.
Might be easy.
Make your life easy.
Make my life easy.
Or you can do random numbers.
Or you can do 1, 2, 3, 4.
It's always an option.
Well, what were the things that the heap does? You need to be able to.
Dynamically allocate.
We need to sift up. Wow.
Fight.
Sift up. And what else do we need to do?
Sift down.
Sift down. All right. Okay. All right. Okay.
And
Oh.
heapify.
And heapify.
Get it?
All right. How would we heapify? Okay.
That's a good question.
Wow. Trying to not do this whole lab for you, but at the same time help you out. So let's go ahead and create.
I'm already dying already.
It's not that bad. It's not that bad. Oh my goodness. Heap equals new int. I will make it 100 just to make life easy. All right. Int size equals 0. And so we'll do stuff like, I don't know, for int I equals 0. Wait, we're going to add those numbers, aren't we? So we want to be able to add to heap, passing in the heap, the size, and then the value. What value do you want to add first? 9,000. All right. Okay, so let's go ahead and write that function. Let's see, void add to heap, passing in the heap, size, and the val. Okay, so what we do, we go heap sub size, not size, that's the size of the whole thing. Yes, that's the total size, which would be, no, the size is actually the position of the current heap, so we want to add it to that position. I got that right. Whew, that was close. So we add it to that position, then what do? Let's make it so we actually change size. Probably should increment size. Then what do we need to do? Let's go up to the board. We put up 9,000. And then we have, let's see, how low on the board do I get to go? 9,000. All right, is that a heap?
Yes.
Yeah, that's a heap. All right, so we won't do anything there. What other value do we want to add? Which one?
1, 2, 3.
1, 2, 3. Make sure we can print this heap. I is less than size, I plus plus. Std c out. Heap sub, whoops. Heap sub I. Space. And then, you know, let's make sure this actually compiles. Could be funny if it didn't. All right, compiles, and it ran. Let's go ahead and print heap passing in the size. All right, that's pretty good. Is that a heap?
Yeah.
Sure. All right. How about another value?
$603.
603. All right, let's run that. Is that a heap?
Yep.
Yeah, it's still a heap. All right, give me another value. I'll give you one. 4, 5, 6. Is that a heap?
No.
Why is that not a heap?
There's 4, 5, 6, and 1, 2, 3. Not comparative.
So what do we need to do?
So,
Sift up. Okay. All right, I'm going to help you out. Int position equals size. We'll put it there, so that's where the position is. So what do we need to compare first?
the parent and the child.
Parent and the child. Where are we currently?
4, 5, 6.
4, 5, 6. So how do we go from 4, 5, 6, which is position 0, 1, 2, 3, up to position what?
Go back.
Minus 1 divided by 2.
-1 divided by 2. All right. Let's see if that
You
works.
do the opposite of that other equation again.
Yep. All right. Equals position -1 divided by 2. Okay. Actually, that's its position. Let's do parent. Oops, that was bad. Parent equals position -1 divided by 2. Okay. So what are we checking? If
The heap at
heap
parent
at parent
is less than the heap at position.
if the value parent is less than child, then our current, then us, then val. All right, so we need a swap. In temp heap sub position. Sub position equals heap of parent, and then the heap of the parent equals temp. Okay, let's see if that works. Probably should add it first. What I add? 4, 5, 6. That looks good. So that moved this guy up here. Got this guy over here. 4, 5, 6. 1, 2, 3. All right. Give me another value.
9,001.
9,001. Thank you. Is that a heap?
No.
So,
What needs to happen?
need to swap it to 4, 5, 6, and then with the microchip.
All right, let's see what happens with our current code. Hit break.
Unless swap once.
It only swapped once. How would we fix that? Ooh, recursion. We could.
And now with the address.
I didn't think of that, but we could have looked at recursion as an option. Yeah,
I have a wow.
yeah, I like recursion. We could do this recursively or iteratively. Let's do it recursively. So what would be the base case here? If position equals, actually is less than or equal to 0, we are done. Right? And then we need to calculate the parent, which is always going to be that. That looks good. And then we take this guy. If the parent is less than the other two, swap. And let's just leave it like that for now and make sure that our basic recursive function is actually working correctly. Okay, let's see what that does. Hey, it does the same thing. So our recursive function is doing well. So now we can get rid of, I'm going to leave that there actually for now. Just for now. All right, so recursive sift gets the base case. The value of the parent's less than swap, but what else do we need to do after we swap? We need to
Make sure that it's all in order.
okay.
So wait, the pointers pointing to one another?
Well, hold on. So what are we doing? We jump into the recursive one. It swaps the 9,000 and the 456, 9001, and the 456. So it takes this 9001, this 456, puts the 456 over here, and 9,001 over there. Now what we need to do?
Do we need to swap it to 9,000?
So we need to, how do we do that again?
Call again.
Call it again. So we just need to call recursive sift up, passing in the heap, and then what's our new position?
Minus, or the minus 1 divided by 2.
Which is
Parent.
parent.
But parent is
Let's see what that does. Hey, there it goes. How about that? Thank you, Malik.
Hold on. Oh, you set parent up with it. Okay.
Yeah. Just so we have some good example, iterative.
Parent.
Let's get that I back in there. Iterative sift up. All right. We still want to calculate the parent on our iterative solution. Let me see if I can remember how this is done. Actually, let's just figure it out. So instead of if, we're going to have while. And then the trick here is now you need to have position equal parent, and then parent equal position minus 1 divided by 2. I think that'll do the same thing. Yeah, it did the same thing. So basically it's just constantly updating a position in parent and then going up again. Of course, up here you're going to need to also check to make sure, let's see, position is greater than 0 and parent is greater than, oops, greater than or equal to 0.
You want to go?
Hmm?
Can you test it out?
Yeah, about ready to. Because now I'm injecting basically the base case up there. Now,
Wait, if parent was equal to 0,
yeah, then you're just checking if you're the root node. That's the root node, right?
yeah.
So then that's fine. And then position.
Oh, yeah, because you're changing it after.
Mm-hmm.
Okay. Just making sure you're putting it in
Now I have a curiosity question. Which one of these is easier?
In terms of compiler or?
No, for you to write and
It
understand.
would depend upon the person.
That's why I'm asking you. For you personally, which one is actually better for you?
like the same.
They're the same for you? That's good.
I need to learn it a little bit more. But okay.
I feel like I would have made more mistakes with the value as far as just comparisons.
Yeah.
Yeah?
I do too.
Do you think so too?
Yeah, I think we probably would have forgotten to position greater than 0 stuff.
Yeah. Yeah, a lot of times the recursive one it's easier to write. So please go for the recursive part. There's no, the performance difference for this class is completely negligible. And in the real world, about 99% of the time, the performance is going to be negligible again. So never be afraid to do the recursive solution.
Do what you're comfortable with.
Do what you're comfortable with. And just make it easy to read. Hopefully this was easier to, I mean, I can make both of them easy to read. What was nice is we always calculate the parent at top, and I think that helped with understanding what was going on. Okay. Let's go ahead and add a couple more. I'll go back to our recursive solution because I actually like that one. What else do you want to add?
7, 8, 9.
7, 8, 9. Then
2.
2. All right, and that'll fill it out. All right. Seven, 8, 9. 7, 8, 9. Do we need to do anything?
Yes.
Yeah.
Need to.
Swap the 600.
Swap the 600. Are we done?
Yeah. 2.
All right. And we add the 2. That's interesting too. How's that?
Short.
All right. Let's see if our code does that. Did it do it? It did it.
Yes.
All right. So there's some confidence that our code is actually working correctly. All right, any questions before we go to the lab? What have I not done for you here?
Shift
Shift
down.
down. I have not done the shifting down.
Sorry.
Hopefully you can see that the shifting down is going to behave somewhat similarly to the shifting up. And we've already written a recursive solution and an iterative solution for you. You'll probably need to keep testing just to make sure that there's no bugs. Let me look at this code real quick. The recursive one, nothing jumps out at me. Let's see. Just calculate position. If position poses less than, then you need to get out and you're done. The value of the parent is less than the value, you can swap them out and then recurse on the parent. Yeah, it looks fine to me because the parent will always be decreasing. So at some point, position has to be at least equal to 0 at some point. Okay. Yeah. So that looks pretty good.
Wouldn't simplification be very similar? Just the parent would be changed.
The parent is going to, yeah, now it's child,
Yeah.
but also what else you need to keep track of? You also need to know the size of your array because you need to know at what point you stop. Because here we knew to stop at 0, right?
Yeah.
Yeah.
So you need to greater than or equal to size and just put possible base case. Possible base case. Just get you started. Well, I say possible because it depends on how you end up coding your heap. Okay? All right. Any questions over what I just went through? All right, great.